And now I hand it over to Marvin, who is going to tell us about the paper Get a Stupid Content Tracker. Thank you.
Hi, folks. Before we get started, I want to say that this presentation is going to be a bit of an odd experience because of circumstances, unusual circumstances today. I received some very sad news a few hours ago. There was a house fire in Yelm, Washington today, and a precious cousin of mine passed away in that fire. Her name's Chelsea Spooner. Now, Chelsea was the kind of person who was unafraid to forge her own path. And one of the more shocking things that she did was to deliberately, at maybe 20 years ago, she burnt all of her own possessions, every last thing that she owned, as a way of breaking with the past. So you can tell that Chelsea is an unusual person. I cannot tell you how many times I returned to the example that she set, and how many times she inspired me to take a path which I might not otherwise have considered. And in that spirit of fearless adventure, to me, there is no better choice this evening than to spend it and share it with all of you, my fellow human creatures. And this will not be a somber evening, even though there may be somber moments here and there. It's going to be fun, and there will definitely be unbridled enthusiasm for the material, because that's how I feel about it. And because there are so many right ways to experience life, and so many right choices that we can make. And the subject matter that I will be presenting tonight may be technical and abstract, but the passion of doing something well is something all the people who gathered here in this room tonight share. Perhaps we might feel that more intensely on some days than on others. But isn't that right and natural for us to feel however we feel about that on any given day? Again, there are so many right choices, so many right paths that we can go down. And this presentation this evening will celebrate one such glorious success. Now, Git is a wonderful example of the enduring power of astute data structure design. And the emphasis on data structure design was entirely deliberate on the part of Linus Torvalds, Git's original author, as illustrated by this quote about data structures in an email to the Git mailing list from 2006. Torvalds prioritized data structure design from the very start. Even the first commit to Git actually established the data structures, which are largely unchanged since that first commit in the Git repository that stores Git itself. In fact, Torvalds had been thinking about version control for many years before Git sprang into being, so he had already largely conceived the architecture and the scaffold around which Git would be constructed. Now, Torvalds was not the first person to advocate an emphasis on data structure design, like you see in this quote here, over coding in software development. Fred Brooks, in the management classic, The Mythical Man Month, writes, "Show me your flowchart," meaning code, "and conceal your tables, and I shall continue to be mystified. But show me your tables, and I usually won't need your flowchart. It'll be obvious." And Nicholas Wirth, who is the author of programming languages including Pascal, wrote an influential book entitled Algorithms plus Data Structures equals Programs. And then there's Eric Raymond from the Art of Unix Programming, who formulated a rule which went fold knowledge into data so program logic can be stupid and robust. At some level, advocating data structure design over coding may not be that profound, really. I mean, data structures are patterns for solving problems. Choosing data structures around which to code up your project just means that you start with some sort of organizing principle in mind, and hopefully the right one. What would it mean, after all, to do the opposite and prioritize code over data structures? I mean, even if you don't start out with a grand overarching architectural scaffold, where do you start? I mean, even if it's something small and incremental, you're still starting from some idea. And what small and incremental task did you take on first? But an approach, specifically in this case, the approach and philosophy of prioritizing data structure design early on, doesn't have to be sophisticated to be worthwhile. Clear is better than clever, robust is better than intricate, and Git, the stupid content tracker per the title of this paper, fits squarely into that tradition. So I would like to pose a rhetorical question now. Those of us in software development use version control systems every day. What is the fundamental problem that these systems solve? Well, what we use these systems for is to help us evolve a project in a controlled manner over time. And I assert that the fundamental job that version control systems must fulfill is to capture the state of the project at arbitrary user-selected checkpoints, which we call revisions, and subsequently to restore the project state at those revisions. We may also want to use the version control system to associate project states with metadata, such as commit messages and tag or branch identifiers. We may want to use version control to introspect project states and to compare them. But those are derivative secondary tasks. Crudely, as long as we can restore different states of the project to different directories, we could use external tools like diff-r for recursive diff to compare those directories full of project state. Everything flows in a version control system from capturing and restoring state. So to solve this problem of version control, of capturing and restoring project state, we have to make a choice up front about how we represent the project state internally, and there are two options. One technique is to store each project state as a snapshot. Now, a naive implementation of this approach is pretty expensive, especially if the project is large, like the Linux kernel, because the space required to store all those snapshots is the average size of the project times the number of revisions. This is naively, of course. So an alternative technique, and a classic way of saving space, is delta encoding. Instead of storing the original snapshots, you store the differences, or deltas, between them. To recreate any particular snapshot, you start from an initial state, which can be simply an empty directory, and then you replay all of the change sets. Assuming that the delta encoding was lossless, then the results after expansion are logically identical from storing whole snapshots. So the technique cannot be differentiated, or the two techniques cannot be differentiated by the information they encode. The advantages of delta encoding manifest when the average size of a change set is small. Then the space requirements are only the size of the average delta times the number of revisions, which can be far smaller than the aggregate size of all the fully expanded snapshots. But this comes at a cost. Say that you want to compare two revisions which are far apart in sequence. If your version control system uses change sets, you need to replay all of the deltas in order to reproduce the differences between the revisions. However, if you've just stored the snapshots, you can access them randomly and compare them immediately. And different version control systems may use one or the other or both internally, but choosing whether the primary internal representation will be deltas or snapshots is a fundamental architectural decision. And notably, Subversion, Git's predecessor as a predominant version control software within a tech ecosystem, uses change sets internally. Think of Subversion as keeping a sequence of patch files. That's pretty much what it does, although those patch files are a little bit more sophisticated. They keep track of not only file-level metadata like permissions, but also information beyond what the file system itself can encode, such as the history of when one file is moved from one location to another. Git, on the other hand, uses snapshots, mostly. It doesn't store whole snapshots, but it does store whole files. And by mostly, I mean it also sometimes uses change sets in certain circumstances. I'll actually come back to that later. But Git, it doesn't store the whole snapshots, but it stores files. If a file changes between revisions, even if it's only by a single bit, Git will rewrite the entire file again as a separate object. Really what Git is doing is a different form of compression. Delta encoding captures differences between project states as a whole. Git's data store instead thinks of the project as the set of all binary blob strings which have ever existed at any time in any file path within the repository. And the underlying data structure that Git uses to achieve this is a content-addressable store. The choice to put a content-addressable store at the heart of a version control system, I assert it was perhaps the most consequential decision in the history of Git's development, and this content-addressable store is the primary data structure that we're going to be studying this evening. Think of a content-addressable store as a hash table where the key needed to look up a value is deterministically derived from the content of the value itself. In Git's case, content blobs are addressed using the SHA-1 hash sums of their binary string. So if a file with content hello world new line appears in a project, it can be found at the address determined by the hash sum for that particular thing, which might be 3B18E5, etc. You get the idea. Where that is the SHA-1 of hello world new line. Now, if the file content hello world new line appears in multiple locations within the source tree, it will still only be stored once in the object data store. And crucially, if the file content hello world new line appears in multiple revisions, it will still only be stored once. And at this point, it's probably starting to click in your mind how Git saves space. Across any given commit, most files do not change and thus can still be referenced in the content-addressable store using the same entry. Therefore, any file which does not change during a commit will not add to the space requirements imposed by a change set. But we still need to record at what file path those blob content strings exist in the project's directory structure. The way Git achieves this is by creating dedicated entries called trees, which represent the contents of a directory. And I put pretty printed content for one such directory on screen. It contains 3 files, hello.txt, promise.txt, and readme.txt. Each line starts with Unix-style file metadata, then continues, that's the 100.644, then continues with the word blob to indicate that it's a plain old file as opposed to another kind of entry. Then we have the SHA-1 hash sum, which identifies the content, allowing us to retrieve it from the content-addressable store. And finally, the string, local string file name. Note that in this tree, the SHA-1 hash sums for hello.txt and readme.txt are identical, indicating that while they exist at different file paths, they contain identical blob file content. We then take the SHA-1 hash string of SHA-1 hash sum of this string describing a directory, the tree content, and that determines where the tree entry lives in the content addressable store. So it lives in the same object database as all of the blobs. And if any of you have ever dabbled in file system design, this idea of implementing a directory as a special kind of a file might be familiar. In fact, Linus Torvalds has expressed that Git's design was heavily influenced by his experience with designing file systems. Now, I'm telling some white lies here because, in fact, Git does not store as much metadata as displayed on this pretty printed output. My understanding is that for files, it only stores the executable bit rather than all those permissions. That's is an implementation deal, I believe, of the index, but in any case, the behavior is that Git is lossy with regards to permissions. But the basic thrust of the idea that trees are locatable in the content addressable store by SHA-1 hashes of their content remains true. It's just that the data itself is not exactly true to what you see when you ask Git to pretty print the tree for you. A commit object in Git is stored using pretty much the same principles. It is represented as a string, a binary string, and then the SHA-1 hash of that string is taken. It's compressed using zlib and then stored in an object in the content addressable store. The data in a commit object, as we see here, includes author name and email, the committer name and email, the commit message, the time of the commit, and also the tree that describes the state of the entire project when it is traversed recursively. Changing any one of these things changes the string and therefore the SHA-1 hash sum, turning it into a different commit. And that's why when you change something like the time of a commit, the commit itself, the SHA changes. You change the author, it changes. You change the et cetera, et cetera. Any one of those things will change the commit. Okay, let's now dive into a Git repository and examine Git's content addressable store. We'll start from the very beginning with initializing a repository and then adding and committing a couple of files. The changes to the repository as the project evolves will be instructive. So invoking git init creates a .git directory which Git describes itself as an empty, quote-unquote, empty Git repository. And let's check out what's in the repo after git init creates that .git directory, proceeding roughly in ASCII-betical order. So first there's a file named head, which has the content /ref/heads/master. We'll go into greater detail about what this does later, but what this file tracks is the branch name which is associated with the current working tree. The only thing you need to know about the directory .git/branches is that it's deprecated. It gives some user options about how to alias remote repositories, but if you don't avail yourself of those options, it doesn't do anything significant. Then there's the file git config, which may be more familiar to some of you. It stores the git configuration information which applies only to this repository. There are three primary locations that the Git application pays attention to, which hold such configuration information, more or less. You can add more, sort of. The most specific one is this file, which applies, again, only to this repo. Then there's the per user one, which lives in your home directory, and then there may be a system-wide one at a place like /etc/gitconfig. The .git/description file holds a single piece of metadata, which is a short description of the repository contents. It's used by the Git web tool, which is now somewhat antiquated. It was an early web-based interface to Git, and it can in some ways be seen as the precursor to GitHub and GitLab, etc. It could be that GitHub uses the description file, but if they do, it's an implementation detail. And because of that, this is not tied to anything in the object data store. And once again, this is sort of something which can be ignored. There's a Git hooks directory where you can put scripts which are called when certain events occur. The git init command stuffs a bunch of sample files into there, but none of them are enabled by default. Hooks are a power user thing, but we're just going to skim past all of them because it's not relevant to the data structures that we're focusing on tonight. There's the .git/info directory, which stores information about the repository. Duh. The most prominent fixture within it is the excludes file, which is one of the files where you can specify git ignore patterns, so you don't wind up committing build artifacts, editor swap files, and similar. And so that's what's I've shown that within git info, there's only the exclude file when you create the directory. And then below that, I just catted the contents of the exclude file, which is a bunch of commented out stuff by default. They have some suggestions that .a and .o files, which are the kind of target files you come up with when compiling a C project, you want to have those in your exclude file. Okay, the Git objects directory, that's where the Git object database lives. Right now it's empty. That info and packer, those are just additional directories. This is where all those blobs, trees, and commit files are going to live. But since we've only just initialized the Git repo with git init, it's right now there's nothing in it. And finally, we have the refs directory, which is where branches get stored. Like the objects directory, it's empty for a newly initialized repository. We'll return to it soon. Okay, that's everything. That's all that happens when you do git init. So we've now examined all the files and directories that get created. And I hope that this exploration helps us to achieve a sense of mastery over git init, at least, and take some of the mystery out of it. Other files and directories are going to be created down the line, so of course this is not a comprehensive exploration. Should you want to find out about those additional files and directories that want to know their purpose, you can consult the repository layout reference documentation, which is available from the command line via Git help, and of course via many places on the web. So you can just typically Google Git repository layout, and you'll wind up with the gitscm.com version of that particular man page. Okay, let's now examine how the repository changes when we git add a file. And to narrate what this sequence of commands is doing, so you just have some idea, this is like a shell, but I didn't want to actually type this stuff because I'm miserably sloppy when it comes to typing. First, we perform this is just as a recursive copy of everything that happened and get init into a new directory so we can compare it later. And then after cding into the new directory, we create a file hello.txt, which contains the content hello world new line, since the echo command adds the new line. Then we git add that file. And a recursive comparison of those two directories using the diff command reveals two new entries two new files created as a consequence of git add. The first is a file called index, and the second is an entry in the content-addressable store whose name is derived from an SHA-1 hash. So Git does sharding in the content-addressable store. So the SHA-1 hash sum for that blob that we've just added is 3b18512, etc. And it creates a directory called 3b, just so you don't wind up with a directory that includes tens of thousands of files or hundreds of thousands of files eventually if you're working on something like the Linux kernel. Here is, let's now look through those files that changed or that appeared. Here is a hex dump of the index file. Hex dump is a utility which allows you to just see sort of the preview binary content or examine what's in there. I'm using a custom format that I cargo culted from somewhere just because I didn't want to see all of the, I wanted to show you two things. First is that the first four letters of DIRC, that's part of a header. It's 12 bytes. It starts off that file. That stands for directory cache. And then there's the file name hello.txt later. The other thing I wanted to show is that the string hello world is not in here. What is actually in there is a bunch of file metadata encoded in binary format. There's the number of index entries, a bunch of data taken from stat, like last modified time, inode, permissions, file size. There's a SHA-1 hash sum in there, but it's encoded as a 32-bit number rather than as a human readable form, et cetera, et cetera. And for the curious, if you want to find out the format of this index file, this is not something which you can get via Git help. But the Git project itself has wonderful documentation. If you go and look at the Git repository at some place like github.com/git/git. And then there's a file, or there's a directory called, what is it? It's slash technicals, or documentation/technical. And then in there's a file called indexformat.git. So you can find it that way. Okay, now here is the actual file content for that the blob file where that hello world new line content ended up at .git/object/3b18535, etc. I've demonstrated two ways to dump the file content here because they show different things. Notably, the content of these files is not just that text content copied in. In the first technique, we use cat to read the file, but we can't just read it directly because first of all, it's compressed using zlib compression. Therefore, we have to pipe it to a zlib decoder. I'm using a little utility that I had to get and compile on the web because there's actually no way to decompress a zlib formatted file that comes on your Mac by default. So anyway, that's what that zpipe thing is. And then we take the out format and dump that to hex dump. And we can see in the output of that the word blob, followed by the length in human readable decimal, ASCII. Then there's that dot actually is a null byte. And then there is the file contents itself including that last dot as a new line. The second technique is the much more user-friendly pretty printing technique using git cat file. You feed git cat file, not a file path, but a SHA-1 hash sum, and it will give you back the content by itself without including either the blob identifier or the length. So it just shows you the content hello world. And again, this file was created, this entry in the object data store was created by git add. It's going to continue to persist in the repository without ever having been committed, though it may at some point become unreferenced and eventually be subject to garbage collection, which we'll get to later. Okay, now we're going to commit the file and see how the object store changes. First, we perform another recursive copy of the working tree, just to copy to a different name directory so we can do the diff-ur later. And then we perform the commit and finally use the diff-ur for a recursive comparison. We see that the index file has changed. That's this. And then we see that there are a bunch of new entries, 5 of them. The index file has just been reset. It's not really interesting to look at it again. The main difference is that it no longer contains the, well, anyway, that's the, it's not, we'll just skip over that. Okay, let's look at the new stuff. First, let's look at the objects directory. That 3b18 file, which contains the hello world new line blob, is still there. Then there are 2 new files, one starting with 6.6 and another one starting with 3.2. The one starting with 6.6 is a tree object, and it contains, it only holds 1 entry right now. The one that starts with 3.2 is a commit object, and I've used git cat file once again to pretty print it here. Cat file -p stands for, the -p is for pretty print. And now we get to one of the most important and revealing files. Now we're outside of the objects directory. We're now into the refs directory. This is one of the most important and revealing files, which is the master branch file. All it contains is a SHA sum. That SHA sum is an identifier for the commit object, which exists in the content addressable store. And this gets at the heart of what a branch is in Git. It's a symbolic name, a human readable symbol, which is associated with a SHA identifying a commit object. And as the project evolves and commits are added to the tip of the master branch, the contents of this file, .git/ref/head/master, is going to change to different SHAs identifying different commits. And in fact, if you want, you can just manually edit that file with a text editor and insert a different SHA. And the result will immediately be apparent as soon as you type git log. Under the logs directory, this was another entry, we now have a new file called at logs/head and a second new file at git logs refs heads master. The content between the 2 of them happens to be exactly identical, and what they are recording is how head and master respectively have changed to point at different commits over time. And this is what actually feeds the reflog feature of Git, is the content of this directory. Finally, there's the commit edit message file, and this is documented as holding the commit message for the commit currently in progress. It's just an implementation detail of git commit. It doesn't have any relevance to the Git data structure design. Now let's try adding the same file content, but at a different location. So we're going to have another file which contains hello world new line, but it's going to be at a different place. So we do that, we create a new, we copy the directory once again, and then we create the directory foo, and then we copy hello.txt to foo/hello.txt. Then we git add foo/hello.txt, and now we start looking at what happens when we compare the last directory state to this directory state, and we see that now the index has been updated, and there's that only in the foo directory, but that's not in the .git directory, that's just in my working tree. So the only thing that's actually changed is the index file. We haven't actually got any new blobs in the content store because it's the exact same file content. After we commit that new file, so once again, we've copied the directory, we've cd'd into the directory. Now we've committed with the message add foo hello.txt. Git reports we do that. Now when I do the diff-r, there's going to be too much stuff to fit on one screen. So I'm just giving you a little preview about what's changing here. Commit edit message is going to change. Refs heads master is going to point at a new SHA. Logs, refs heads master is going to have a second entry added to it. Head's going to have another entry to it. The log is going to have another entry added to it. And then there's going to be 2 new files in the objects directory as well. So what we see here is the most recent commit message, which changed in commit edit message. It no longer says add hello.txt. It says add foo/hello.txt. Once again, this is just an implementation detail of git commit. The index file, which changes the commit staging area, has been updated by the commit, whatever. Now, we also have a new tree object, which is the top thing here, here. And then we also have a new commit object. You can see that it's commit object because it has committer and not just the file stuff that's in there. So the tree object is notable because it illustrates that trees are a recursive data structure. It contains both a blob for hello.txt and a subtree for the foo directory. That's this. And one thing that's interesting, though, what's missing from the object database? We don't have a new tree for that subdirectory. And does anyone even want to venture a guess as to why not? Why isn't there? So we have the new file, hello.txt, only had to be in one place. Yes?
Well, Git doesn't store directories. Well, they don't. Never mind. Sorry. I think I was going down a different path. If you have an empty directory, Git won't store it, but this isn't an empty directory.
That's true. Yeah, you're right. That's true, but it's not what is actually the case here. Does anybody have a guess of this? I'm happy to spoil it for you.
Is the content of hello.txt identical to hello.txt? That wasn't clear.
That's the content of foo/hello.txt is identical to the content of hello.txt.
I guess then it would be a pointer to the original object.
So you're right. The trick here, and this is the deal, is that not only is hello.txt only requiring a single identical object or a single object within the data structure, but the directory that we committed before that was up1 only had a file called hello.txt. This new directory, this new tree, also only has a file called hello.txt. The directory contents are identical. Therefore, the tree representation of that as a string is also identical, and therefore its SHA-1 hash sum is identical, and therefore it doesn't need a new entry.
So this tree file, or I think it's a file, right? This tree file is not referencing itself; it's referencing a former version of itself as a child.
You can think of it that way. Yes. Yeah. Yep. That's right. That's what this tree is. This 664B. If we were to go back a few slides back, we'd see it was that number.
But for the root.
For the root. Exactly. Yes. And now it's actually as a subtree. And this was by design. Git is deliberately aware of when subtrees are logically equivalent, because that makes for fast tree comparisons, which was one of Torvald's design criteria for Git. And I'm going to speculate now, although I don't know this for sure, and this is related to your point from earlier, that one of the reasons Git is kind of crappy about actually showing the file history is because it doesn't encode into tree structures the history of how files move around, unlike Subversion, which is actually quite good about showing you don't have to add git log -- follow, for example. Subversion just will give you the history of a file, even as it's moved from different places in the tree. Git is not so great at that. And I think that the reason that is because if you added that history information, then directories which were otherwise completely identical in terms of their logical content would cease to be equivalent. And that would spoil Torvald's criteria for having subtrees be equivalent even when they're located at different locations and perhaps have different histories. Okay, that commit object is interesting too. It actually has a field that our early commit did not, although I didn't go field by field in there. The first commit, what it has now is a parent. Our first commit did not have one of those because it was an initial or root commit. Now, the vast majority of your commits are actually going to look like this because you only have that first one initial commit. Well, that's not true. You actually can have any number, an arbitrary number of root commits in a Git repository, depending on how many branches you have, or you can just create them and then merge them later, etc. But the main thing to know is that every every commit object in Git has 0 or more parents. If it has 0 parents, it's a root commit. If it has 1 parent, then it's part of a linear history. And if it has 2 or 3 or 4 or more parents, then it's a merge commit, where lines of development are deemed to have come together. Okay, now what this shows, although it's a noisy slide because it's the diff is noisy, really there's only one line that's changed here. This is the refs heads master file, which is where the master branch is stored, and so that is just showing that the SHA-1 hash sum has changed. I also had I took the opportunity here to squeeze in git/head, and that hasn't changed. It's not changing at all. It's not changing from commit to commit. That's because the head is telling you what branch is associated with the current working tree, and you can think of it as a pointer to a pointer. So when you use head, it says, okay, so when you use head like in a command on the command line, it says, okay, head is actually the specially named thing. I'm going to go look in this file, .git/head. It's going to tell me what file within refs to go look at. And then I'm going to look at the SHA-1 hash that's in that, and then I'm going to use that SHA as my commit identifier. And finally, there's the log entry. This tracks everything that head has pointed to over time. This powers the ref log, and we can see that it's added more information that actually is showing you the previous commit followed by the current commit. The previous commit followed by the current commit. You're going to see that those two are equivalent. Then some metadata about that. Once again, this is the ref log information. Yes?
Is this not captured if you were to trace the commits back? Is this just a more efficient representation of that? Or is this capturing something fundamentally different? It is capturing something fundamentally different. This is the information. So when you do something like check out a new branch, or when you when you reset the current commit, what that does is that information is not recorded in the history of the project. It's not in the linear Git or the commit ancestry tree. That's stored in the log. Now, another thing that's important is when you push to a remote repository, all those refs go to the remote repository, but none of the logs do. So this is exclusively local information. But what this allows you to do is actually, this is another set of root objects to prevent stuff from being GC'd. So this is the reflog feature. We have limited time to get through everything tonight, but it's actually this is one of the features that, along with behavior like git add, immediately adding stuff to the repository, which makes it so that a surprising amount of stuff which otherwise might be accidentally misplaced can actually be recovered. There are lots of destructive things you can do in Git, but a lot of times a surprising amount of state. If you have somebody who understands this stuff well enough, they can go in and find that stuff for you again. Okay, that's enough of that. So you may have noticed tonight, enough of typing on the screen for now at least. You may have noticed tonight that I've been using some fairly esoteric Git commands, especially git catfile-p to pretty print an object. There are a number of other such low-level commands for interacting with the content-addressable store, such as git revlist, git diff tree, and so on, which you probably have not used. In the paper that I'm theoretically presenting tonight,
They're always just a point of departure for us. Git advocates talk about, and elsewhere, Git advocates talk about the difference between plumbing and porcelain commands. The plumbing consists of these low-level commands, such as git cat file, et cetera, et cetera. And the porcelain is generally a higher-level interface, stuff like git commit and git log. And you can actually piece together something like git log with all of its like 40,000 flags, using all of the low-level stuff like git rev list and stuff like that. And because these low-level commands are exposed, it's possible to design alternative, different user interfaces by combining those low-level commands in different ways. For example, we could actually do away with the index. It's not really needed as a dedicated file because it's not part of the object database. It's a staging area. So consider one crude proposal. We might just have a command which commits all the current differences in the tree to the object store immediately. That would be less flexible, but also be somewhat simpler because we would just bypass the index. And to show my hand, I'm actually working on one of the reasons I chose this particular paper is I'm working on an undo mechanism for a music composition application which uses a text-based file format, and I'm building the mechanism on top of the Git repository format for the undo mechanism. So, and it's indeed going to commit changes directly rather than go through an index staging area. I'm basically, implementing a small version of Git because this stuff isn't really that hard. And so these sorts of things are only possible because Git's data structures are so simple and have proven so stable, just as Linux Torvalds intended and hoped for. Okay, yes, go ahead.
Okay. I'm familiar with the term porcelain. I thought it meant it's a particular flag you give a git command, and it's supposed to be stable over time, so that you could put it into scripts, and your scripts aren't going to break. Does that ring a bell to you?
You could. Well, what that implies is actually that the plumbing has the freedom to break.
Right.
That may indeed be, and if that's the case, then I'm actually a little bit wrong about whether or not you could recompose your own versions of your own porcelain. You could, but it would be fragile.
Yeah, exactly.
So then, the thing is, in the paper, they actually talk about alternative porcelains. There was one that was, I've forgotten what they were called. They aren't popular anymore. But you can think of actually GitHub itself as an alternative porcelain with lots of extra stuff like pull requests that are not part of the Git application itself. So you have different user interfaces. But the idea here is, the thing is, even if I'm wrong about the plumbing commands being stable, the data structure itself is stable, shockingly stable, honestly, considering it's literally the first commit actually has the documentation which is still basically right for what a commit object is, what a tree object is, and what a blob object is. And the basic formats have all been stable ever since 2006. Yes?
Was Git self-hosting from the beginning?
So that first commit, yes. It had to, of course you had to actually get it to a point where you had to, you still had to type something. You still had to type, there had to be an initial file before it could become self-hosting. So the answer is no, because the egg had to come first, not the chicken. Okay. So now I'm just going to do a touch on the pack files briefly, because this is something which shows up in the index and people may have heard about. When the object data store gets very large, to save space, Git is going to encode the oldest commits using a compressed format. And they may, in fact, be delta encoded. So this is where I talked about earlier that actually Git would use deltas. This is where. That's amusing because Git deliberately emphasized random access over compactness by choosing snapshots over deltas as its primary storage model. But it's deemed an acceptable, it's an optimization. And it's acceptable because most action takes place as space-saving optimization, because most of the time you're doing stuff, it's in the you're dealing with recent history, not ancient history. So we accept the inefficiency for the occasional command, which has to deal with events from the distant past for the sake of some space saving. But once again, it's just an optimization which Git's architecture can withstand, rather than a fundamental design choice. Okay, now let's think for a bit about how tracing garbage collection might be applied to our objects database. And unfortunately, if those of you who are not familiar with tracing garbage collection, I'm not going to have time to explain that in detail right now. So if you're not familiar with that, this may go past you a little bit. Sorry about that. Tracing garbage collection in Git works basically the same way it does for any garbage collected language like Java or Go. You start, though, with all the files inside of the refs directory, all of the refs heads masters, and then all of the refs. So one thing I didn't do, but just for the sake of time, is I never actually went through and showed you what happens when we do git branch. When we do git branch, it would have, or git checkout-b. And say we did git checkout-b dev to create a new branch called dev. What that would actually do is create a file called refs heads dev, which would have a SHA inside it. It would sit alongside of refs heads master. So those files, those SHAs, those form the root objects that from where we start tracing. And then we follow the commit history from those commit objects, find all the parents. From all of the, at some point we've got full trees of the entire history of the project across all of the branches. Those commit objects in turn reference all blob and tree objects which have existed in the history of any current commit. And then there's also the reflog stuff. So once again, you might get, start from the reflog to see if you traverse what you can find. And so now, if when you perform a garbage collection, you've now got your everything which has been marked as referenced, and anything else which exists in that. Say you had git added a file, but then had gone and reset and not used that version of that file in an actual commit. You'd added something else to the file after you've done git add, then git add again before git commit. The first version of that file still exists as an object in the directory because git add changes the objects database. And that file is now unreferenced because it's not in any particular commit. That blob is now unreferenced. So it has the potential to get garbage collected. But also note that Git GC is very conservative because, you know, we're not dealing with like memory here. We're dealing with just some file space. So, I mean, wasting file space is fine for the most part. At least on the order of text files in a typical project. I mean, if once you start adding binary files, then you all may think about actually deliberately GCing your project if it helps. But then, so now you perform the, so the Git GC doesn't kick in for a long time, and even then it never deletes objects within a certain time frame, which I think is at least a couple of months. Okay. So, okay, right. So, next, we're going to talk about another characteristic of Git, which is of really paramount importance, is the choice that of being decentralized instead of centralized, or distributed instead of centralized. And this has grand implications for collaboration in particular. And arguably, it's a data structure choice as well, but again, I'm here primarily to talk about the content-addressable store tonight. And I don't think that this is really that closely related. But one thing that has become clear is that centralization is just an emergent phenomenon with regards to project development. There still needs to be some canonical repository. Of course, Linus Torvalds actually would have understood this intimately even when Git was just a gleam in his eye, because he is not only a superior coder, but a superior community manager, and is trying to organize how the entire community interacts when he's designing Git, not just designing something locally. And of course, he would have known that whenever you have a group of people, there still needs to be a canonical repo which holds a canonical history. And so, amusingly, GitHub often emerges as a single point of failure when for a distributed version control system. And every time GitHub goes down, a group of people gathers on Hacker News to celebrate that irony. But from a technical standpoint, I think that Git Annex and Git LFS are interesting extensions to Git, which happen to have the effect of making it more centralized. What those do is that the problem that you have is that when you add binary files to Git, it tends to explode the size of the repository if you version those over time. So if what Git Annex and Git LFS do is store your big binaries on some resource server somewhere. And there's really only one obvious way to implement this, which is, and this is related to the content addressable store once again. So you have, it's very straightforward. Ordinarily, when a tree object is being checked out, it references a blob, and you go and get the blob content from within the object database. But if you want to save space when dealing with giant blobs, then you store a symbolic reference instead within the local repository and the actual content on some centralized resource server. And then you can fetch big blobs lazily on checkout instead of fetching all of the big blobs when during the repo cloning. You just need, in the repo cloning, all you need is the short symbolic references, the IDs. Okay, we're coming to a finish here in a couple of slides. And let's review some of the design criteria from the paper. A key requirement that Torvalds has was to lighten the burden on the integrators who merged proposed changes into the Linux kernel. Since the Linux kernel is a comparatively large project, speed for large-scale operations around a large project with many files was paramount. We've talked about how random access makes comparison and diffing of branches inexpensive compared to summing up deltas. That makes it easier for the integrator to see what's being proposed in a patch set, even if in the case of ongoing development. Though we might wish that for all evolution of our code bases to be incremental, sometimes long-lived branches happen nevertheless, and being able to randomly compare, or have a random access to snapshots to compare them is a big boon to the project integrators. We've also seen that commit application is relatively lightweight because not much needs to happen in the object database in order to apply a commit. And here's where the distributed nature of Git really shines, because it's certainly faster to apply commits to local branch and update a few files in the objects database than it is to talk to a remote server, like you would have to in a centralized system like Subversion or BitKeeper, or et cetera, et cetera. And so now, or I'm not sure I got that right about BitKeeper, various CVS. And so now we've seen, okay, with these issues in mind, we can see how those who play the integrator role in Linux kernel development benefit a great deal from Git's design, but they're not the only ones. Git's simple design structures benefit us all. And so now, if I have done my job right, you might be thinking, that's it? That's all there is to it? The Git command line interface is very complicated and has an endless number of options and flags. Using it typically doesn't lead you towards an appreciation for the simplicity and elegance of the data structures at the heart of Git. But if you can, by going down an alternate path, familiarize yourself with those data structures, all of a sudden a whole new world will open up before you. Thank you.